So we're going to talk a little bit about carboxylic acids, then we'll talk about Lewis acids. The carboxylic acids are organic acids which contain a COOH group, which you can see in red there in the structure below, where the R is some sort of carbon-containing molecule because hydrocarbons are your organics. The COOH is a carbon double bond oxygen single bonded to an OH group, where you've got an oxygen single bonded to a hydrogen in that group. These are all weak acids, and only the hydrogen attached to the oxygen is the one that ionizes. The example we've been using, because it's very common, is acetic acid CH3COOH, which may not be how it was written when you took a first semester course, but it's often written that way to show you which hydrogens are acidic. If we talk about Lewis acids and bases, according to the Bronsted-Lowry model, remember the acid was a proton donor, but now the Lewis model focuses on electrons, where a Bronsted-Lowry acid can be considered as an electron pair acceptor. And so that's what we're going to consider as the Lewis acid. It's the broadest definition, but it's a Lewis acid, it's going to be an electron pair acceptor. The base would be the donor. So usually a Lewis base would have non-bonding electrons it could donate. Also, it's the broadest definition in that it need not necessarily contain H plus or hydroxide, and it need not necessarily be aqueous either. And that's a very popular when you take organic chemistry. Lewis acids usually have an incomplete octet. For example, boron or beryllium compounds tend to be Lewis acids because they have vacant orbitals in which electron pairs can be donated. Compounds with pi bonds can also act as Lewis acids, like carbon dioxide is a Lewis acid. Well, you probably have heard in lab by now that we boil the water to get the dissolved carbon dioxide out, and it raises the pH to closer to 7. And it's because that carbon dioxide reacts with water to produce carbonic acid. And because it has electrons from the pi electrons to donate to form bonds with hydrogen. And so they act as Lewis acids in that there's an electron pair donated to form these extra bonds instead with hydrogen and oxygen, instead of moving around the hydrogens explicitly. Metal ions can also be positively charged and attract water molecules via the non-bonding pairs on the oxygen. And if they're transition metals, they're donated into vacant d orbitals. Aluminum can also be somewhat acidic, and you can have electrons donated into the vacant p orbitals in that case. But you get a metal-water interaction. These hydrated metal ions act as acids. The number of waters of hydration will vary, but what's important is that you got, for example, this iron with 6 waters of hydration, 3 plus charge. It loses one of the hydrogens, and so you end up with a FeH2O5 and then an OH, but with a positive 2 charge. So that OH is hydroxide, which has a negative charge. Ka, 2 times 10 to the negative third, so not necessarily a wimp on the acid scale, but still a weak acid. pH increases as the size of the ion increases. That is, a 2 plus ion is not going to be as acidic as a 3 plus ion. So sodium is less acidic than calcium. Zinc is less acidic than aluminum. Usually your plus ones and a lot of your plus twos are not very acidic. Turns out plus one ions tend to be very weakly acidic to neutral, where calcium 2 plus is ever so slightly acidic, but so much that a lot of people ignore it, where aluminum is fairly acidic. Lewis bases tend to donate electrons. For example, nitrogen-containing compounds like ammonia commonly act as Lewis bases, even if water's not present. Other substances like hydroxide and anions of weak acids can often act as Lewis bases by donating electrons. Again, very popular in organic chemistry where you're often not in water.